Welcome to this lecture series in linear algebra. In this lecture, we'll learn the complex spectral theorem, which is a very important theorem in linear algebra. And let us recall some of the things that we will need. So suppose we have a vector space over any field, it doesn't have to be real or complex, and T be a linear endomorphism on V. And let Mx be the minimal polynomial of T, and let us say it splits in this fashion. Well, I shouldn't say it splits. What I want to say is write it as the product of irreducible polynomials in this fashion, where M1 up to Mr are pairwise distinct irreducibles. So fine, with that information we can show, or we have shown earlier and discussed, that the vector space V decomposes as follows. This is the primary decomposition theorem. And the other interesting fact is that T is diagonalizable if and only if this splits into distinct linear factors. One way to express that is this. Alright, another thing that we will need is the following. If V is a complex inner product space and T is a linear endomorphism on V, which is normal, then the kernel of T is same as the kernel of T star. And another simple fact that T minus lambda I is normal whenever lambda is a scalar in the base field, which is the field of complex numbers. So we will need these facts. Here is one problem for practice. And now let us get started. So first we will prove something about the eigenvectors of normal operators. And when I say operators, I mean the same thing as endomorphism. It's the exact same thing. It's just a difference in terminology. Okay, so let V be an inner product space and T be an endomorphism on V, which is normal. I don't think I will need the fact that, or the hypothesis that V is complex. This should be true for any, either real or complex vector space is what I'm going to say. So now let's say lambda and mu are two distinct eigenvalues of T, and let U and V be corresponding eigenvectors. All right. So then here is the claim. We claim that U and V are orthogonal. So eigenvectors corresponding to distinct eigenvalues of any normal endomorphism are orthogonal, is what we are trying to show. So here is the proof. Say lambda is non-zero. Why can we assume this? Because lambda and mu are distinct, so at least one of them has to be non-zero, and we can just work with the non-zero one. Without loss of generality, we may assume that lambda is the non-zero one. Both may be non-zero, of course. Okay, so now we have this thing is equal to, which by the fact that Tu is equal to lambda u, what have I written? This is lambda u. We have, this is Tu. Use the property of the adjoint. Okay, now this I will say is equal to something that I will have to justify, is equal to mu bar V. So I have to justify this equation. Give me a second. So what happened here is the following. What we have is T is normal, which implies this is normal, as we discussed in the recall, which implies kernel of this guy is equal to kernel of its adjoint. But what is the adjoint of that thing? That is equal to this. Now since T minus mu I is 0, t minus mu I of v is equal to 0, we have, which is nothing but this equation, right? So therefore t star v is, again I missed a term, this is v. So t star v is mu bar v. T star v is mu bar v. So that explains it. And we continue. Okay, so what we have shown is this guy is equal to that guy, but since lambda and mu are distinct, it follows that this must be 0. So dot dot dot, you finish that. So the conclusion is the following. The eigenvectors corresponding to distinct eigenvalues of any normal operator are orthogonal regardless of whether we are working over a real or a complex vector space. Alright, so now let's move on. So this is a very nice fact that if we have a complex inner product space and a normal operator on it, then it is diagonalizable. Any normal operator on a complex inner product space is diagonalizable. So this can be proved in multiple ways, but I will present a proof that I really like, which I learned from Professor Namrata Khetan. Right, so let's see what is the proof. So we will show that the minimal polynomial of t splits into distinct linear factors. That is how we will go about this. So let mx be the minimal polynomial. Okay, and then we may say, so say where these are pairwise distinct, and of course each ki is at least 1. So since we are working with a complex polynomial, meaning a polynomial with complex coefficients, all the reducible factors of this guy are linear, so the factorization of mx will look like this. What we want to show is that each ki is equal to 1, not just at least 1, that's a given, but we want to show that it is equal to 1 for each I. Because then we can use the criterion and establish that t is indeed diagonalizable. Okay, so assume on the contrary that it is not. So let's say ki is greater than 1 for some I. So then here is the important deduction that we can make from here. Then there is a vector v such that So why is that? Just use the primary decomposition theorem. We have seen this kind of thing many times, but what we are doing is just use the fact that we have this decomposition 1 to r kernel t minus lambda j I kj. We have that. So if this were false, then either so basically I'm saying just consider the ith component here, and if it has a positive, an exponent greater than 1, then this should hold, and I'll let you mull over it. We have done this kind of thing earlier. Let me not get bogged down by this, otherwise this flow of the proof will break. So just realize this fact. This should also be intuitively obvious. Okay, so now let WB is equal to that. So then W is non-zero, but that is the case, right? Because of this, we immediately have that. But now again, since kernel of this and the kernel of the adjoint of this are exactly the same, why? Because t is normal and hence this is also normal. So we get this is also 0, which is nothing but saying this. We have that. And now, finally, just consider this. What is this inner product? This is clearly 0 because this is already 0. And therefore, this is 0, which implies, by using the property of the adjoint, this is 0, which now by definition of W, this is 0, which means what? Which means t minus lambda I v is 0, but that contradicts the pink thing. This pink thing is contradicted by this, and therefore our assumption that ki is greater than 1 should be false. And we have established this yellow thing, which establishes the diagonalizability of t. That's it. So that proves the diagonalizability of the endomorphism t. Finally, let's move on. So we have the complex spectral theorem that we will show now. It'll just fall out of what we have done. So here is the proof. Yeah, so what is the statement before we prove it? Fix a complex inner product space and fix a normal endomorphism on it. Then there is an orthonormal basis of V consisting of only eigenvectors of T. Right? So if we drop this normality, if we drop this normality hypothesis, then what we can say using Gram-Schmidt is that there is an orthonormal basis of V with respect to which the matrix of T is upper triangular, but with the normality hypothesis, we can say something much stronger, that it is diagonalizable, that it is, there's an orthonormal basis of V which witnesses the diagonalizability of T. Okay. So you could go via the Gram-Schmidt route, no problem with that. You start with any basis which diagonalizes the endomorphism T, so any basis which witnesses the diagonalizability. And then perhaps using Gram-Schmidt you should be able to show it, but let me do this in a more straightforward way. So let these be all the eigenvalues. Okay, then by what we have proved, by the fact that T is diagonalizable, we have the minimal polynomial of T is this. So mx is the minimal polynomial of T. Let me not write that. So by the primary decomposition theorem, we have the vector space is decomposing like this. Okay. And what we have already shown is that any two vectors corresponding to distinct eigenvalues are orthogonal, and hence you pick this guy or any other guy in this direct sum, those two subspaces are orthogonal to each other, because this is the set of all the vectors which are eigenvectors corresponding to lambda 1 and so on. So this is actually a decomposition of the vector space V into pairwise orthogonal subspaces. Okay, so now what we do is pick Bi as an orthonormal basis of the ith part. So maybe let Bi be equal to maybe Mi, I don't know. Let's say Ti be an orthonormal basis. Of the ith part. So now one just needs to check that if you just concatenate all of these things, then you get an orthonormal basis, of course. Why? Because all these are pairwise orthogonal. So if you pick something from Bi and something from Bj, then those two things will also be orthogonal. Okay, so then basically check that this thing that I'm going to write, this is an orthonormal basis of T of V consisting of only eigenvectors. Of our endomorphism, and that finishes this proof. That is exactly what we wanted to show. Alright. Finally, here is a remark. So this is called the complex spectral theorem. And now here is a remark which I would like you to pause the video and read and understand. We have proven this, but I would like you to read and understand this on your own. Okay, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.